terms of either polar covalent, nonpolar covalent, or ionic. So you need to know generally some of these numbers to help you kind of figure out questions like that, okay? And I can post some more practice questions for that too. So I would classify the bonds to be polar covalent, just based on the electronegativity difference alone. In each case, which bond is more polar, and then it says indicate in each case which atom has the partial negative charge. So I'm looking at dipole here, and then I want to know, is the BCl bond more polar or less polar than the CCl bond? So boron chloride, boron monochloride, if I'm looking at that on my periodic table, I see that there's a larger amount of space between these two than there is between carbon and chlorine. So because of that, automatically, because of that larger space, I immediately want you to think that would be a bigger electronegativity difference. So because of that, I would say that the boron monochloride bond is what's going to give me a more polar bond versus carbon and the chlorine bond, okay? So if I'm thinking larger space means greater electronegativity difference, means the bond is more polar, so that would be this one, versus these are a little bit closer together. So if we're thinking about which atom has the partial negative charge, let's go back and draw the dipole for each of those then. So I have boron and chlorine. I know chlorine is 3.0. If I looked at my chart on that electronegativity table, and then boron is 2.0. So that electronegativity difference is 1. Since this has a greater electronegativity, that's my partial negative. Boron is my partial positive. Or, let me draw my arrow. Head going to the more electronegative, tail at the electropositive. I can do the same thing for carbon and chlorine. Chlorine, we said, was 3.0, and then carbon is 2.5. So that electronegativity difference is 0.5. Remember that we said that BCl is going to be a more polar bond, and I proved that too by showing that electronegativity difference. So we can think about it logically using the periodic table, or I can show it with math, and either explanation will be fine. So chlorine is the more electronegative than carbon. Same thing here. Arrow goes to the more electronegative, positive end on the electropositive end, or a delta positive, delta negative. You do not have to do both. The only reason I'm doing both is just to show you you could have done one or the other, okay? So arrow is fine, or the deltas are fine. I just want you to know that both are acceptable. I have phosphorus and fluorine bond versus phosphorus and chlorine bond. Well, fluorine is going to be fluorine is the most electronegative element, and then chlorine is just right underneath it. So since I'm pairing with the same first element, then I would say I have PF, and let's just actually look at their electronegativities. So PF versus PCl. So we know that fluorine is a 4.0, chlorine is a 3.0, and then phosphorus is 2.1. So just based on those electronegativity differences alone, PF is going to be the more polar bond. Fluorine is more electronegative, so let me give it the delta negative. Phosphorus will get the delta positive, and it would be the same situation just with chlorine for the next one. Okay, the last one, it says, which of the following bonds is most polar? I would like you to do this one, and then let's circle this answer, or somebody remind me that we'll go over this one the first thing when we have this for homework, okay? Polar covalent bonds. When two atoms share electrons unequally, a bond dipole results. We just talked about this. We have a dipole, meaning that we have partial charges. The dipole moment, which we will symbolize with the lowercase Greek letter mu, produced by two equal but opposite charges separated by a distance r, is calculated. So I want to see what is the moment, or what is the attraction like between this negative and this partial negative, partial positive charge. That's my goal. I'm really thinking about that attraction, okay? So I can calculate it by taking charge Q times the distance that's separating those particular charges, which we're going to call R. So mu is measured in debye, which we're going to symbolize with a capital D. And then 1 debye is equal to 3.34 times 10 to the negative 30th Coulomb meters. Okay, so C represents coulombs because that's my unit of charge. And then, of course, then we would have meters, and that makes sense because mu is calculated by taking charge times that distance, which should be in meters. Okay, so let's look at maybe what an example of that would be. So this is just me quantifying without using electronegativity. It's me quantifying an actual dipole moment. So I don't think that you'll have to do or see anything like this on the AP test, but it's just a nice little thing to also know, just because your college professors will want you to know this, or know how to do this, okay? So I have chlorine monofluoride and iodine monofluoride are interhalogen compounds, which means compounds that contain bonds between different halogen elements. Which of these molecules has the larger dipole moment? So chlorine monofluoride versus iodine monofluoride. So I first just want you to tell me chlorine monofluoride or iodine monofluoride. If I had to guess without, or not guess, but use logic, use your periodic table without the electronegativities as help, figure out which one of these would be the more polar bond. Which one of these would be the more polar bond, okay? Make your prediction. We can actually do math to go along with this. And that's what they want us to do here. So which one would have the larger dipole moment? You don't even have to do math. They just want you to tell me logically using your periodic table. Okay, let's say that the bond length in HCl is 1.27 angstroms, which is 1 times 10 to the negative 10th meters. So it's 1.27 times 10 to the negative 10th meters. Calculate the dipole moment in device that results if the charges on hydrogen and chlorine atoms were a positive one and a negative one. Okay, so how do I do this? What are some things that I know? I know to find dipole moment is mu equals Q times R. So charge times the distance that's separating them. I have a positive 1 charge and a negative 1 charge. So that positive 1 or negative 1 is actually the true charge on an electron or on a proton. And that charge is not just going to be thought of as 1. Remember, I told you we use that as just our own scale. That charge is really going to be 1.60 times 10 to the negative 19th coulombs. That's the technical charge of an electron or of a proton, okay? I also know a distance they gave me that the bond length was 1.27 angstroms. But that's the same thing as saying 1.27 times 10 to the negative 10th meters. And I want Coulomb meters because remember 1 debye is equal to 3.34 times 10 to the negative 30th Coulomb meters. So let me do this for my R because that's the bond length that's separating the hydrogen from the chlorine. So I have that 1 charge, either positive 1 or negative 1, I'm just thinking about its magnitude. So I have my charge times the distance separating them, which is 1.27 times 10 to the negative 10th meters. Okay, if you do that, we're going to get a number. I do not have a calculator with me right now at all. Yeah, no, don't have a calculator. That's working. Okay, so you'll get a number here, and that's in Coulomb meters. But I want my dipole moment to be in debye's. I want it to be in that capital D. So when you have that number, erase this really quick. So I have my number in Coulomb meters, and then I know 1 debye is equal to 3.34 times 10 to the 30th Coulomb meters. 10 to the negative 30th, sorry. So I would take whatever number we found here, divide it by the 3.34 times 10 to the negative 30th. Should get around like 6. Like 6 point something. because this would be to the negative 29th, and I'm dividing that by negative 30th, so it should give me, I should get a fairly small number, so it should be like 6 point something, okay? So mu equals 6, and then whatever the decimal is, divides. So that's how I would do a problem like that, okay? Again, I don't think that you're going to see that on your AP test. I've not seen it on your AP test ever, but just so that way we know how to do that, we do know how to do it. Usually we'll be focusing on using electronegativities, okay? We just said the greater the difference in electronegativity, the more polar the bond is. So if electronegativity difference is great, dipole moment should also be the same. So I should see that, or it should also be fairly similar. So electronegativity difference here, I see I'm going from hydrogen fluoride to hydrogen chloride to hydrogen bromide to hydrogen iodide. So I have hydrogen attached to all of the halogens, and this is just showing a trend that's happening down that halogen family. I see that the electronegativity difference as I move down that group decreases. We said that as we move down a group, electronegativity difference or electronegativity decreases. That should make sense. Dipole moment will be the exact same. These are just two different ways to measure the polarity in a bond. Bond length, though, let's talk about that. So as I move down a group, electronegativity difference decreases. Bond length increases. So hydrogen fluoride is a much smaller bond than hydrogen iodide is, and I want you to think about why. I have more electrons, so that means I have more energy levels, I have more shielding here. The attraction here is not as great, thus separating out the bond. So it should make sense logically that as electronegativity difference goes down, I don't feel as much attraction between either the nucleus and those electrons, so the bond length is going to increase in response to that. That should make sense, okay? So let's differentiate between ionic and covalent bonds. We treat ionic and covalent cases separately, but it doesn't mean that we think about them as being just all ionic or all covalent, because sometimes we see that there's a difference, or we see that it's on a spectrum, really, because we treat acids as though they're ionic, even though they have covalent characteristics as well. So when covalent bonding is dominant, it's typically in molecules, so I'm going to see two nonmetals. I also know that covalent bonding is dominant when I have a low melting point or a low boiling point. So that's another trend. And then they also exhibit non-electrolyte behavior. So even though acids are made from two nonmetals, usually they act like molecules, so the bond may be covalent, but acids will exhibit, when they're dissolved in water, electrolytic behavior because they dissociate. So it's I can think about them as an electrolyte because they dissociate and they become ions. When ionic bonding is dominant, usually what we see are brittle or extended lattices. So I see these really large crystal structures. And then I also see that those ionic solids could be brittle. They're very high melting points, very, very high melting points. And that's because we've actually had a transfer of electrons. So because of that, that Coulombic attraction is much stronger than just sharing a pair of electrons. And then we know that ionic bonds are highly electrolytic, meaning that when they dissociate in water, they will dissociate or break apart into their ions, so that can carry current. How do we recognize the types of bonds, or how do we distinguish what's ionic versus what's covalent? You usually do this in one of two ways. If it's a metal and a nonmetal, or if it's a metal and a polyatomic, it's ionic. Versus if it's two nonmetals, we typically think about it as being covalent. I think you're fine sticking with that. It's fine. But there's another way that we can think about them too, and that's by using electronegativity difference. And when I use electronegativity difference, that's where I have to start thinking about these things in terms of a spectrum, okay? Guys, we did Lewis structures while I was gone. We'll do some more Lewis structures again. I'm going to make another small video for you to watch about covalent bond strength. I may not even assign that until the next day, so I will see you guys tomorrow. I hope you have a really wonderful night. Bye.